Alright, we're ready now to do lesson 9.3 on the Pythagorean Theorem. This is a very important theorem which you'll study again in much more detail when you get into geometry. There was an ancient Greek mathematician lived many years ago, like in the BC rather than the AD, by the name of Pythagoras. He was a philosopher, he was into studying theology, science, but perhaps is best known for being a mathematician. Pythagoras and his buddies came up with the idea that if you have a right triangle, by the way, a right triangle means it's a triangle that has a right angle, right? And the two sides that make up the right angle are called the legs of the right triangle. The third side, which is always going to be the longest of the three sides, has got a fancy name. It's called the hypotenuse. A right angle, remember, is 90 degrees. Anyway, Pythagoras and his buddies came up with the idea, which we call the Pythagorean Theorem, that said for any right triangle, the sum of the squares of the lengths of the legs, so like if I call this leg here, if I call this A, and if I call this leg right here, if I call this B, okay, it equals the square of the length of the hypotenuse, which I'm going to call C. Or A squared plus B squared equals C squared. A squared being one of the legs, the lengths of the leg squared, plus B squared, the other length of the leg squared, is equal to the length of the hypotenuse squared, C squared. If you've ever watched the movie The Wizard of Oz, towards the end of the movie, when the scarecrow gets his diploma from the wizard, he kind of points to his head and he says something that sounds very smart. What he's trying to say is the Pythagorean Theorem, but he messes it up because he doesn't say a right triangle. He says a different type of triangle, an isosceles triangle, which messes up his whole idea, which means in that case that he didn't get a brain. Anyway, we're going to show some applications of the Pythagorean Theorem next. Okay, we'll start out with a story problem. Kyle's building a ramp for his skateboard. He builds it in the triangular shape as shown. How long is the ramp? In this case, this distance right here. Well, because it's a right triangle, and because I know 2 out of the 3 sides, I can use the Pythagorean Theorem to find the third side, which in this case is the hypotenuse. These, remember, are the legs because they make up the right angle. So I could call this A, I could call this B, I could call this A, I could call this B. That part's not important, you can interchange those. But I'm going to find here my unknown, which I am going to call C. So in this case, I'm going to write down that 5 squared plus 12 squared equals C squared. 5 squared is 5 times 5, 25. 12 times 12 is 144. And if I add those together, I get 169 equals C squared. Now remember, we did equations like this a while back in the last lesson, where we solved for C by taking the square root of both sides. So if I take the square root of both sides, now remember, we're not going to get plus or minus here because our C is a length, it's not going to be negative, but we can see that C in this case, no pun intended, is equal to 13. So it is 13 feet long. I used the Pythagorean Theorem to find one of the sides that's missing. Remember, with the Pythagorean Theorem, you have to have 2 out of the 3 sides to do this. And it has to be a right triangle. The next 4 examples are more the same, but just that they're already set up for us and they're not in story problem form. You're to find the unknown length in simplest form. The reason that this is written down is, although this one came out to be a nice integer, that's not always the case. Sometimes we get a square root that doesn't simplify completely and give us an integer. We have to write it in simplest form. In this case, I have A, I'm looking for B, and I have C, which again is the hypotenuse. So I know that 18 squared plus B squared equals 30 squared. Now I have to maybe grab my calculator for this. 18 times 18 is 324, plus B squared equals 30 times 30 is 900. Now I'm going to subtract 324 from both sides. Now to do that, we've solved equations before. Whatever you do to the left, you have to do to the right, and I get B squared is equal to, now I've got to be kind of careful here, 8, 9, and that's a 6, and that's a 7, and that's 576. Now as it turns out, you might not know this, but 576 is a perfect square. You would find that when you take the square root if you use a calculator, because it will come out to be a nice integral amount. So in this case, I get B is equal to 24, because 24 times 24 is 576. All right, similarly here with example B, I'm going to find one of the missing sides here in the right triangle. In this case it's a. I know that a squared plus 20 squared equals 25 squared. A squared, now 20 times 20 is 400. And 25 times 25 is 625. So kind of what I'm doing here, if I subtract 400 from both sides, I get a squared is equal to, that's 225, and I like that again. 225 is a perfect square. If I take the square root of both sides, I'll get 15. A turns out to equal 15. Now that's not going to be the case with the next example. It's not going to come out to be an integer. I'm still looking for a, just like I was here, but in this case, a squared plus 12 squared, b squared here, these are the legs, equals 14 squared. 12 times 12 is 144, and 14 times 14 is 196. So if I subtract 144 from both sides, I get a squared is equal to, now in this case it looks like it's going to be 52. So if I take the square root of both sides, I get a is equal to the square root of 52. Now, the square root of 52, 52 is not a perfect square. That's supposed to be a 5 there. It looks a little bit more like the letter S. But the square root of 52 does simplify because 4 divides into 52. So like we did in the last section, or a section or so ago, I'm going to simplify this by breaking this apart as 4 times 13. A is equal to the square root of 4 times 13, which is 52. That's the square root of 4 times the square root of 13. That's 2 square roots of 13 here. And that's my answer. That's what a turns out to be. Now if you punch it into a calculator, you're just going to get some long decimal. So you're better off in this case making sure of your work by simplifying the radical. And the last one I have up here says that I have a and I have b, but I don't have the hypotenuse, kind of like the very first example up here. So 17 squared plus 8 squared equals c squared. Again, Pythagorean theorem to find this missing side, in this case the hypotenuse. 17 times 17 is 289. 8 times 8 is 64, equals c squared. Now if I add those together, oh goodness, 3 carry 1, 5 carry 1, I get 353. 353 is equal to c. So if I take the square root of both sides, I get c is equal to the square root of 353. Now let's see, 4 doesn't, it's odd, 9's no good, 25's no good. 49 is no good. Let's see, 81 is no good. 121, 160. That one just does not simplify. That's as far as that one goes. That's my answer. I kind of thought of all the perfect squares that might divide into them, and none of them did evenly, so I'm going to leave my answer in that form. So if you have 2 sides out of the 3 of a right triangle, you can use the Pythagorean theorem to find the missing side, the third side. Now there's a kind of a reverse, or what we call the converse of the Pythagorean theorem. It's where we say, hey, if we have a triangle whose sides are a, b, and c, and if a squared plus b squared equals c squared, then we know that that triangle must be a right triangle. So we're kind of reversing it. If we know a squared plus b squared equals c squared, then we can show that that triangle is indeed a right triangle. And again, this is something you'll see again when you get into your geometry class. Okay, we're going to use the converse of the Pythagorean theorem to work the next examples. This is determine whether the triangle with given side lengths is indeed a right triangle. So we have these 3 lengths of the sides. Now it doesn't say which one is A and which one is B and which one is C, but we know if it is indeed a right triangle, then the longest side of the 3 has to be the hypotenuse, if this is true. So this would have to be C, and you could call either one of these A or B. So I'm going to call this one A and this one B. I'm going to write 2 squared plus 4 squared equal 5 squared. That's the question. Well, 2 times 2 is 4. 4 times 4 is 16. 5 times 5 is 25. No, this is not true. So, no, it's not a right triangle. Now I'll try the next example. Again, the longest side has to be the hypotenuse. This will have to be C, and I'm going to call it A and B respectively. So I'm going to write 9 squared plus 40 squared equals 41 squared. Now the numbers are starting to get kind of big. 9 squared is easy enough. Even 40 squared is not too bad because 4 times 4 is 16. So 40 times 40 is 1600. But I don't know what 41 squared is off the top of my head. I do, but I'm just acting like I don't. 41. And I'm going to square it on my calculator, and I get 1,681. Well, if I add those together, I get 1,681, and this is indeed equal. So in this case, the answer is yes. It is a right triangle. One more example. Again, the longest side would have to be C, so I'll call that A and B, and I'm going to write 7 squared plus 24 squared. Does that equal 25 squared? 7 times 7 is 49. 24 times 24 is 576, and 25 times 25 is 625. If I add those together, is indeed this true? Well, let's see. That's 5 carry 1. That's a 2. 625 equals 625. That one's true. So the first one was not a right triangle, but the other two are examples of the sides of a triangle that would be a right triangle. Now I'm going to kind of step back and go back to the Pythagorean Theorem, because I just want to show you an example or two here of a problem where they don't draw it out for you. They don't have the right triangle drawn out for you, but they say it's a right triangle. Right here it says it's a right triangle. You're to find the third side. Well, that means we'll have to use the Pythagorean Theorem. I'm going to go 20 squared plus b squared equals 29 squared, since I have a and c. Over here, I'm going to write a squared plus 36 squared equals 45 squared. And then I'm going to go ahead and find these. I might get radicals that don't simplify completely into an integer, so I'll have to deal with those accordingly. 20 times 20 is 400 plus b squared equals 29 squared. Oh, I'm a little rusty here. 29 squared. I'm going to grab my calculator. I'm going to square that out. I know it ends with a 1. It does. 841. So if I subtract 400 from both sides, we did problems like this just a minute ago, I get 441, and then I think 441 is 21 times 21, but let me just double check. Yep. So if I take the square root of both sides, I'm going to get 21. That one does come out nice and neat. So that would be B, the missing side there in the first example. Over here, the numbers are getting bigger. I have a squared plus, now 36 times 36 I think is 1,000 and some change. Let's see, 1,096. Nope, I pushed the wrong button here. Let me try that again. 36 squared is 1,296. 45 times 45. That's a pretty good size one. That's 2025. Now I subtract 1,296 from both sides. I get a squared is equal to, and again I'm just going to be a little bit lazy here. I'm going to punch it out on my calculator since I already have it close by, and I get 729. Now 729, is that a perfect square? Well, you know, I think it is a perfect square. It's not one that you think of right off the top of your head, but if you use the square root button on your calculator, this turns out to be exactly 27. So I thought maybe I might get a radical there, but as it turns out, both of them worked out nicely. Alright, the Pythagorean Theorem is really, really a key idea in mathematics. You'll see a lot more of it in geometry, but for the problems that you're going to be working on here in this class, remember to practice, practice, practice.